Hey guys, got an exciting episode for you today. Going to be making a major addition to that indoor micro grow. So previously you guys seen me playing around with these cheaper Chinese cob chips. And my main motivation there was, first of all, to do the analysis. I had access to the spectrometer for a little while through my friend. And I thought it was a great opportunity just to check. And it was just, kind of fun for me. And the second part of that I was interested in is to kind of test what the lower limits of light the plant could need and still do okay. And obviously if you're going for high yields, high production, don't do that. That's a bad idea. But anyway, it was just something I was interested in. And I think those chips are alright. I mean, you kind of get what you pay for, and for the cost, I think they could be worth it in some applications. The drivers are complete crap, that's for sure, but there's an appropriate application for everything. But as you guys can see, what we're going to be adding now are going to be some horticultural light group quantum boards. So I have a 4-pack here of the 120s, and so it's like a warm white 3000K color temperature. So when I went to buy these, their site was actually completely sold out of everything. When you watch this, that might not be the case. And I wound up getting this 4-pack on Amazon for, I think it was $125. Let's take a look, see here. They got a bit more weight than I was kind of expecting from the videos and the pictures. Kind of a good thing. Help them stabilize on the wires that I'm going to hang them on. So HLG 3000K. Pretty recent production. I'm in the middle of December 2017 right now. And you can see the chips that they're actually using here are the Samsung 561C, so that's LM 561C if you want to look up the actual chip. And I think they're the 0.3 watt bin. I think I mentioned this before. You might come across this term binning in LEDs. Basically what that refers to is the inconsistency of production of even the highest quality fabrication plants of these devices. And so what they do is they have a line and they take each LED that comes off the line and they run set current through it, and then they measure basically the voltage or the wattage, whatever, and class them, or i.e. bin them based on the performance. So there might be 0.3 watt ones, there might be 0.5 watt ones, or whatever, however they separate them out, I'm not sure. But that's a standard process in the LED market. Okay, so what I'm going to do is go ahead and run 2 of these boards in series. So we're going to be splitting the voltage and keeping the current constant. Okay, so no heatsink required if backside has contact with air, which will be fine. These will be right at the top of my tent in my 2x3x3 micro tent. But it should be fine. There's fans up there anyway. So they included a bit of wire here so you can hook them together. And they have these quick connect types. You can also get the DC plug ones for wiring multiple boards in series. This makes the most sense. Before I bought these, I did some research and I found a channel on YouTube called LED Gardener, and he did a bunch of reviews of all of these HLG boards. And I think on the HLG website, in fact, they show some of his results for this QB120, where he measured the PPFD, so that's the micromole per meter square per second. Alright, so let's just kind of map out what the design of these 2 boards in our setup will be. And again, all credit here goes to LED Gardener. I'm just using his data. He's very kind to do that analysis, I think, and provide it for the public. That's a great service. So initially he had this board, which by the way comes in a kit called HLG65, where they're running it at 65 watt. I'm going to be running the two boards at 100 watt total, I think. Anyway, so LED Gardener, he drove it at about 2.11 amp, and he measured a PPFD of 243. Hope you guys can see that. Let me just zoom in a little bit for now. 243, and the unit on that is typically written like this, which, you know, scientists would hate this type of writing. If you were to follow the rules of algebra, this would be basically micromoles per meter squared seconds, like that. Sorry, I'm gonna move that up. Or better yet, this is the most non-ambiguous way, in my opinion, micromole times meters -2 times second -1. All of those are technically the same. Anyway, and then at the max of the dimmable driver he was using, he got to 2.43 amps, which is kind of what I'm expecting. And in the center, he got 275. And I'm just going to abbreviate to micromoles for now. So I think this was when he just first turned on the fixture, and as it warmed up, then he took his measurements, and that's what you'll see in his videos. That's what you'll see on the HLG website, and it's basically like a 2x2 grid with data points throughout it, and that's what I'm going to be going off of it. And I'm just going to simplify down here a bit so we're not looking at it in two axes, but rather just one axis. So basically his results, if I could just summarize them, if we look at the center, so right below the fixture, I'm going to call that C, he was measuring about 290 micromoles. Then if we go 6 inches away from that, he was getting about 250. And I'm, again, I kind of rounded these around to mostly just summarize his results. You can see the actual data on his video. And then at 12 inches from the center, it was around 180, and that's where he stops measuring, just a 2 foot wide square. So from center, another foot in this direction, and this direction. What we can start thinking about now is that, okay, if we put these fixtures such that they were their footprint, oh, and by the way, this is important, this is at 18 inches from his detector. So in other words, 18 inches from the light to the canopy. So if we put these two lights with them basically where their footprint is just touching, that would basically put 180 here, and then 180 from the one that's next to it. So that would give us a total of, what, 360, right? It would kind of make a hot spot now where the brightest intensity isn't at the bottom of each of the boards, but rather in between them. That's all right, I think. That would be perfectly workable, but what if we idealistically kind of wanted to make it an even intensity throughout the tent? So we would have to offset it. So the next light, the 180 position wouldn't be here, but somewhere a bit to the right. So he doesn't have this data, but if I could just estimate here at 18 inches, and LEDs drop off quite quickly, so it's got to be below 100. I'd say, I don't know, 60 micromoles. Again, I'm just guessing this value. He didn't measure that. So then we could say, okay, if we put the next light, the edge of it at the 12-inch away from the center position here, that would be 180 plus 160, that would be 240. It still wouldn't, it would be too low now that compared to this value. So somewhere in between, I would guess. So about, let's see, a 6-inch, about 3-inch offset. So if we put the other light, how would we do this? The other light would not be here, so it would be 12 inches here. 6 inches, center. So this is light number 1, light number 2. And So let's see, the 12 inches, we have 180 from the second light, and 250 here, 290. And again, we're estimating the 18-inch position to be 60. So then I guess we could kind of estimate this spot to be, I don't know, around 110, just for the sake of ease. And I think this is starting to look like something that would work. So let's kind of just assume, again, ideal conditions where we could just add the intensities together in the overlap region. So here in the middle of our fixture, we would have 290. And then, again, we estimated this point here as 110, so that would be 290. And then, let's see, we have 180, 250. So I don't know, this would probably be around 220. I'm just making numbers up, guys, here. It doesn't really matter. So 280, 280. And then, you know, maybe the next spot down, it would be less than 60. I don't know, 20. So I don't know, let's call it 270. And then we're back to 290. And same thing here. So we got 290, 270, 280, 290, 290. Pretty close. Pretty darn close for the total intensity, I would say. So let's just think about then, okay, well, does this even make sense? Because I'm already starting to see an issue here. Because think about it, we got a foot here. We got another foot here, so that's 2. And then another one there, so that's 3. Are we even going to be able to fit this into my 3 wide foot tent? If we use 3 inches here, so 1.5 inch. So between center and center, we have 13.5 inches between board centers. Wait, no, sorry. 13.52 center, so it's 13.5 times 2. So 27 inches between board centers. So, okay, so first of all, with that value, we can do 27 minus... Oh, by the way, these QB120 boards are what we need this value now. I think they're 11 inches by 9.5, so slightly wider than that piece of paper, but pretty close to square. So if we're 27 inches between board centers, that means there's still half a board on each side, so a total, and let's just go with the low width here. What is that going to be? Minus 10 plus half. So 17.5 inches between boards. Okay, so that will be the space. So in a 36-inch wide tent, there's 18 inches. Okay, so this isn't going to make sense, I don't think. And finally, the value you really want to check is that if we have 27 inches between centers, and then we still have the rest of the boards to add to that. So this is kind of the minimal. Uh-oh, here we go. What is that? Between edges, right, of the board, so the outer dimension there. And that's a 1/2 inch wider than our tent. So that's a problem. So even if we did want to do this setup to try to replicate this kind of even spread of light, it's not possible with 3-inch offset. We would have to do at least 3.25-inch offset. We put it 18 inches above our plants. Is 290 even going to actually do anything for us? So that's the next thing we should really consider, is how many micromoles per meter square per second does a plant actually need? And just roughly speaking, I looked up some values. In the vegetative stage, the kind of lower end of optimal growth. So again, what I was saying with that, where I was messing around with the cobs, this is going to be way below this. But if we want to be in optimal growth, this is where you need to start and go above this, basically. So that's about 350 micromoles. So, and then I guess we can make a value for something that's kind of more like optimal. And for vegetative phase, that's around 700. And again, I'm very much ballparking here. And then finally, let's, while we're at it, go ahead and make a category for CO2. And again, the only way you're going to get efficiency out of adding CO2 is if you basically increase everything. The light intensity, the humidity, the temperature. You need all of that to go up to increase your photosynthetic rate. And so only if you're going for this extreme case where you're trying to get the highest efficiency with the CO2 method, then you might go up to 1,000. And while we're here, let's go ahead and do the values for flower. And what you have to really consider here is that when you're going from vegetative state to flower phase, you're typically going from 18 hours to 12, so that's a reduction of 1/3 of the amount of light. So you have to basically increase the intensity up by 1/3 in order to compensate for that. That's why the PPFD in flower is higher by about 33% for flower relative to vegetative stage. It sees the light for that much shorter time in the day, so the light needs to be that much more intense. And again, helps with penetration for dense flower formation. And so the lower end for the flower should be about 500. And then about 1,000 is considered closer to optimal. And maybe if you're crazy going to CO2, you could go up to like 1,500, but that's, you know, really pushing it. Our 290 doesn't even seem that significant anymore. And what I think I want to aim for is probably around the 500 mark, because that would really put us right in the range for optimal growth for veg, and we could still probably get away with flowering something once in a while. Or, you know, since it's going to stretch, it'll probably stretch into the higher intensities anyway as it gets closer to the light than 18 inches. LED Gardener was kind enough to also do the same analysis at 12 inches. So let's consider that then. Because obviously as you get closer, the intensity goes up. Because they're LEDs and it's a board that's where they're spread out, what you'll see here is that it increases much more in the center, closer to center, and not that much on the outside because your footprint shrinks so much. So now we're talking about 12 inches from sensor. And so if we consider these same values at the center, he's talking about values closer to 480. So we've got a pretty large jump here, and we're getting quite close to the values that we really want in the 500 range. So 480 at the center, and I am summarizing the 6-inch position at 340. And then 12 inches from the center, we're at about 200. So you can see that this value and this value are pretty close. So once you get towards the outside of the footprint, it doesn't really make much difference whether you're 12 or 18 inches away. Now if we go ahead and put up our second light right up to the edge of this footprint, we're gonna have 200 and 200, that's 400, so it's actually less than our center. So in this case, we wouldn't want to offset it in this direction as we just spoke with here. Now if we're really targeting what we actually want for a good grow, we want to offset it in this direction, right? So that we're really doubling up these values. And if we're aiming in the 500s, just for convenience, I mean, if we put this 200 here, so basically an offset of 6 inches in the other direction, be 340, center, 480. Okay, so now we got 540, 540, and so on. So that's getting real close, I think. Again, just for shits and giggles, let's just estimate this 18 value. I don't know, 60 or so. Right, just to make this convenient. Okay, so then we have another 18 inches here, 60. Okay, so that's now, let's see, 18 inches, so that's half of our tent basically. So we have another 18 inches on the outside, and then it's the walls. Okay, so what does that mean for the actual lights? So here's the center of one, here's the center of the other. Again, if we're going with the 9.5 dimension, that's 4.25, so that puts us, roughly here. This one out here somewhere. If we start going in this direction now, 6 inches, 12 inches. So this goes to here. This is 340, 200. It's going to be a long video. Again, I'm just trying to make sure I account for everything here. That's the kind of whole point of permaculture, is that it's all about the design. You can spend all of your time, or 90% of your time and effort, in this kind of planning stage, rather than, dealing with mistakes and kind of trying to come up with solutions on the go. Kind of that reactive approach. This is much more a proactive approach. And you can do all of this. You can do a cost projection without buying or getting a single thing. Again, LED Gardener provided this data for us, so why not use it? Okay, so 6 inch, again, 340, 200. So where is the edge of our tent here is the question. So let's just do the math here real quick. What do we have here? We have 18 inches between board centers, right? From here, 6, 12, 18, from center to center. So then if we go 18, let's just do the same type of analysis we just did before. 18 minus the width of the board will give us this spacing here. So that's what, minus 10 plus a half, 8.5 between boards. And then in the other directions, plus 9.5. Let's see, that's plus 10 minus a half, 27.5. Edge to edge. So that's from this point to this point. And finally, what we really want to know. Okay, well, we can already use this value to figure it out, but let's just go ahead and do this. 36, which is our total tent length, minus our fixture edge to edge, leaves us 8.5 inches space divided by 2, which equals 4.25, 4.25, right? Outside space. So the real question we want to know is how much is it, I guess, from the center to the wall, right? Yeah. So that's going to be half of a width, so it's going to be, sorry, 4.5, no, sorry, 4. Let's see, 9.5 divided by 2, 4.75, sorry, plus the outside space. Okay, so we do have all the values. So that's 9 inches from center, sorry, my pen is running out here, to wall. So that means that our wall on this schematic that we've drawn is right here. And right here. So you can see how now the lights will be arranged here. So let's do our summary now. Obviously, we kind of set this up. 200 put 3, 4, 540, 540, 540. This is convenient. And then, so let's see. This one will probably not the top line here, the left light, probably won't have much of a footprint going out this far. I would guess it would be very minimal. So it would be 340 here from this right side light. But remember, our wall is here and it's Mylar. So this 212 inches away, which is what LED Gardener actually measured, that's effectively, you can't go in here, so it's going to be reflected back in. So I am going to go ahead and say that, well, I was just writing through the camera there, that feels weird. That's about going to be 540 as well. So just doing a quick analysis, with the 12-inch detector, our size of the tent, trying a couple, just possibilities, this looks like it's going to do really well for us. So then now let's consider the height. So this is kind of in the X direction. The Y direction should be pretty good, I think. So in the Z direction, if we put the boards right up to the top of the tent, or pretty close so we still get some ventilation, that means to our floor is 36 inches, right? It's 3 foot by 2 foot by 3 foot. So now you'll probably see the real limitations of microgrows, why they can be really challenging. So, okay, so what does that mean? If we're going from the 18-inch footprint, or sorry, 18-inch from detector scenario, that would basically take out half of our height for the light. And it would only give us 18 inches for the plant, the pot, and maybe a stand or whatever, everything else. Okay, so that would make things real difficult. Let's just see what that looked like. So if we had 18 inches here, 18 inches here. So if you're using kind of a smaller pot, and let's just say it's 6 inches high, kind of a standard half 6x6 pot or half gallon, I think. Or you can maybe even go to a smart pot, like a large size smart pot, like a 3-gallon smart pot, and just roll down the sides so it has a low profile but goes out far. Okay, so 6 inches here. In this particular scenario, we're saying the light is going to go down to halfway. That means that we only have 12 inches of plant space. Now that is very small. So basically, you're going to have your trunk. You're going to start topping it, and it's going to branch out. You're going to get a nice and even canopy, like that. And if you're doing it, this kind of style of training, you're basically wasting that 12 inches. Because if we're talking about vegetative plant, it's getting its, intensity. And then if we switch to 12 hours for flowering, it's going to stretch up into this higher intensity that it wants up here. So it's going to flower up here, and we're going to strip off all the larvae stuff down here. So that's basically not going to contribute to our yield whatsoever, these lower 18 inches of height. I mean, the pot height, obviously, you don't really consider it contributing, but, this is kind of a waste. So the alternative to that, obviously, one of the things that people would do then is switch to a different training technique, where you keep the stem as low as possible and you just start branching it out straight from the beginning, leaving it low, trying to get this type of canopy. And so now if your pot is 6 inches and maybe you can do this within 6 inches, that's possible, but obviously it's going to take some work. Now that actually frees up a whole 6 inches for you to grow your plant even larger before it hits this point and then stretches up here into this space for flowering. Okay, so now if we reduce this to 12 inches, not only do we get this if we do the training, but we get another 6 inches of space because now our light intensity only coming up to that point. And again, this is where the light would be, up here. So I think that makes sense because based on the numbers we did, if we go with this setup, we can lower our light down a little bit And you know, this is great that I'm considering now, because this kind of tells me how long my wires need to be at the longest point to make this happen. So yeah, I think that's gonna work. Let me see, is there anything else we can think of? I think that's gonna do it. All right, well, that's a super long video. Stay tuned for the next one in the series, where I am going to show you the driver I'm gonna use, and we're gonna all put it all together and turn it on. All right, guys, thanks for watching, and we'll see you in the next one.